The low-altitude economy relies on autonomous aerial vehicles conducting complex tasks, but navigating high-density urban environments requires split-second precision. The limiting factor for these vehicles is strict: size, weight, and power, known as SWaP. A drone has a physical limit on the hardware it can carry. To avoid buildings and other aircraft, they must process raw perception data, like high-resolution video and LiDAR, in real time. This requires massive computational capacity. The standard approach is to offload that processing by sending raw sensor data to cloud servers located hundreds of miles away. The physics of networks present an immediate barrier. The round-trip delay of sending heavy video files to a centralized cloud and waiting for instructions creates a lag. A 200 millisecond delay means a drone moving at 50 miles per hour travels blind for 15 feet. In a city canyon, that delay causes an immediate control failure. Engineering networks to bypass this specific bottleneck is the primary focus of research detailed in this special issue of the IEEE Internet of Things Journal. Since it is impossible to mount a supercomputer on a lightweight drone, and the speed of light to the cloud is too slow, keeping these vehicles airborne requires a structural change to where computing happens. This framework is known as Augmented Edge Sensing Intelligence. It replaces the drone-to-cloud model with a three-tiered continuum: the device, the edge, and the cloud. At the device layer, the drone handles only immediate raw sensing and split-second physical actuation. It acts as the eyes and the muscles. The local edge server, positioned on a nearby cellular tower or rooftop, acts as a proximate brain. It handles the sub-millisecond cognitive loads required for navigation. The distant cloud server manages asynchronous, long-term foundation model updates. This distribution of labor shifts the heavy processing demands off the drone's chassis and integrates them into the surrounding infrastructure. Consider the requirements of navigation. When UAVs fly between skyscrapers, satellite GPS signals are often blocked. They rely on visual inertial odometry, or VIO, mapping their spatial location using onboard camera feeds and motion sensors. Processing high frame rate video to track a flight path frame by frame drains a drone's battery and maxes out its processing limit. The tripartite architecture solves this through edge-enabled VIO. The drone stops processing the entire visual image. Instead, it extracts basic feature points, isolating high-contrast edges, and offloads the tracking math to the edge server below. The edge computes the position and fires back actionable navigational vectors. The drone receives spatial updates within the millisecond window required for flight stability, while significantly reducing its onboard energy consumption. Decoupling the act of seeing from the mathematics of understanding proves critical flight control can be safely outsourced if the compute node is close enough. Even with a proximate edge server, the wireless connection between the drone and ground remains a choke point. Bandwidth is finite. Researchers mitigate data bloat using knowledge graph-enhanced triplet semantic communication. Rather than forcing raw video pixels through the wireless pipe, the system transmits the mathematical meaning of the environment. This semantic extraction shrinks the payload, freeing up bandwidth and keeping the channel clear. However, edge servers experience fluctuating processing loads, meaning a drone must also determine when to transmit its data. This requires a multi-agent actor-critic queuing framework. It operates like a triage system, toggling the computational load between local processing, the edge server, or the cloud. The framework continually calculates energy and latency budgets, dynamically routing tasks to prevent system overload. Semantic transmission and dynamic queuing act as the regulatory system of the network, ensuring the connection to the edge remains functional under high data loads. That data load increases as we scale from a single UAV to a dense, heterogeneous swarm of delivery and transport vehicles sharing the same airspace. Managing dozens of independent flight paths simultaneously requires a hierarchical conflict resolution framework to prevent collisions. Using graph transformer-based reinforcement learning, the system maps the entire swarm as interconnected nodes, identifying potential collision points. The edge server processes this topology centrally, resolving the conflicts and pushing safe flight paths to every vehicle in the sector. However, this interconnection introduces a vulnerability. If a single compromised drone feeds bad telemetry to the edge, it could misdirect the entire swarm. This threat is known as data poisoning, which occurs when faulty updates are injected during the network's federated learning cycles. To defend against this, the system runs model similarity checks at the edge. It evaluates incoming data against the consensus of the swarm, isolating and rejecting the poisoned packet before it integrates. Autonomous coordination at scale depends on verifiable data streams. Edge-based security filtering maintains the reliability of the instructions the swarm depends on. This system allows drones to extract semantics, while the edge resolves conflicts and blocks anomalies. The heavy cognitive lifting happens in a real-time loop between vehicles and edge servers. Simultaneously, the cloud refines foundation models using verified data supplied by the edge. Researchers formalize this unified approach as the co-drone framework. This framework shifts autonomous navigation into a collaborative process, leveraging combined resources of the entire infrastructure. It circumvents the weight and power limits of the vehicles. They don't need larger processors because the calculation is performed on the ground. The result is a persistent, intelligent airspace, an environment that processes reality on behalf of the vehicle navigating through it. By augmenting sensing intelligence at the edge, the UAV transitions from an isolated computer into an agile node operating within a flying neural network.